Google Cloud Storage promises extreme durability. But that ironclad durability won't protect you from the wrong storage model. Today, we map object, block, and file storage so you never put the wrong data in the wrong place. Think of your office. You've got filing cabinets for documents you access by name, a hard drive inside your PC that the operating system sees as a raw device, and a shared network drive multiple colleagues can mount at the same time. In the cloud, these translate directly. Object storage is the filing cabinet. You store files, objects in buckets, and retrieve them over the web via a URL. That's Google Cloud Storage. Block storage is the virtual hard drive you attach to a VM. That's persistent disk. File storage is the shared network folder that multiple VMs can access simultaneously using the NFS protocol. That's Filestore. NFS stands for Network File System, an industry standard that lets multiple computers share files over a network as if they were local. When you mount a Filestore instance, a folder on your VM becomes a window into that remote file share, so every VM can read and write the same files at the same time. Keep this mental model. It makes every architecture decision trivial. Here's a real web stack. Your front-end VMs boot from persistent disk. That's block storage. They pull shared CMS assets, content management system, a platform that stores editable website content, from Filestore, a managed NFS mount that every instance can access in parallel. For static images, videos, and user uploads, you often store them in cloud storage, where they can be served through a global CDN, content delivery network that caches assets close to users for faster delivery. That's not an abstract list. That's exactly how you'd architect a high-traffic site. Now let's zoom in on the most versatile piece, cloud storage. Cloud storage is an object store. The two key nouns. Bucket, a globally unique container in a specific location, and object, a blob of data plus metadata. Cloud storage objects are designed to be immutable. You replace the whole object rather than appending. The URL follows a predictable pattern built from the bucket and object name. Bucket names must be globally unique across all of Google Cloud. Pick one already taken and creation fails immediately. That's the most common beginner trap. So your first command should always be a bucket creation attempt in Cloud Shell. If it says, bucket already exists, you've collided, pick another. Spend 5 minutes wrestling with that. It'll stick forever. Price per gigabyte, abbreviated GIB, per month drops dramatically as you move from hot to frozen data, from 2 cents to a fraction of a cent. But the trade-off is minimum storage duration and retrieval fees. Standard has no minimum. You can delete after an hour. Nearline requires 30 days, Coldline 90, Archive 365. If you delete an archive object after 10 days, you still pay for 365. All storage classes share the same high durability. Google Cloud's infrastructure ensures identical protection against hardware failure, and they all belong to the same object store, so you work with the same API and G-Cloud commands regardless of class. The only real difference is cost, minimum storage duration, and retrieval fees. So cost optimization is purely about matching access frequency to the right tier, never about sacrificing safety. Let's test your storage class intuition. Which class would you pick for data you keep for a year and rarely access? Pause. The answer is Archive. Archive storage is designed for data stored 365 days with the lowest cost. Here's the mental cheat sheet. Standard for anything that needs to be fast. Nearline for the stuff you check once a month. cold line for the stuff you hope you never need. DR. Archive for the stuff you legally must keep for years. And remember, all four are backed by the same industry-leading durability. So you're not choosing between safe and cheap. You're choosing how often you plan to touch the data. This is a lifecycle policy. You write one set of rules that says, after 30 days, move to nearline. After 90 days, move to cold line. After 365 days, either archive or delete. No cron jobs, meaning no recurring scheduled scripts that you'd set up yourself. The lifecycle policy runs automatically on Google's infrastructure. One policy applies to a whole bucket, and you can even use conditions like matching object prefixes. Set it once, forget it, and watch your bill shrink automatically. Here's the trap that costs beginners real money. You store 30 GB of monthly logs in Standard for 30 days. That's 60 cents. Then your lifecycle rule kicks in and moves the objects to nearline. Congratulations, you just saved nothing because you already paid the full month's standard price. The trick. If you know the object is infrequent from day one, set a lifecycle rule to transition objects to nearline as early as possible. Many teams use an age of 0 days. Now that same 30 GB costs 30 cents instead of 60 cents for the month. The rule triggers the moment the object lands, not after you've already been charged. Always ask, do I ever need this to be hot? If the answer is no, freeze it at birth. Quick checkpoint. Which storage class requires your data to be stored for an entire year before you can delete it without fees? Pause for a moment. The answer is archive. Nearline makes you wait 30 days, cold line 90, and standard has no minimum. Now, let's secure your storage with IAM, Identity and Access Management, GCP's permission system that controls who can access your resources. You need to send a 5 GB video to a client for 24 hours, but they don't have a Google account and you definitely don't want to open the entire bucket to the world. The solution is a signed URL. Using the G-Cloud Storage Sign URL command, check the current documentation for exact syntax. You can create a time-limited link that grants access to a single object. Anyone with the link can download the file, no Google account or bucket-level permission required. After the expiration, the URL simply stops working. It's like a self-destructing ticket that gives temporary scoped access without proliferating credentials. Here's how you set a lifecycle policy right from the console. First, click Create Bucket. Give it a globally unique name. Pick a region like US Central 1 and hit Create. Then open that bucket and head over to the Lifecycle tab. Hit Add a Rule and configure it to move objects to nearline after 30 days. That's the tier for data accessed about once a month, and delete them after a year. This is Cost Autopilot. You define the policy once, and cloud storage automatically transitions your data to cheaper classes when it gets cold. Fire up Cloud Shell, and let's run through the essential GSUTL commands you'll use constantly. First, we create a bucket with GSUTL MB. The bucket name must be globally unique, so add some randomness. Then we upload a tiny text file. Notice the ACL command. We're adding an entry that gives all users read access. That's an access control list, a legacy permission model, and this ACL instantly makes the object public. In production, you'd use IAM, but the example shows how quickly wide-open access happens if you're not careful. Finally, according to common usage, GSUTL RMR deletes every object inside the bucket. To actually remove the empty bucket itself, you'd follow with GSUTL RB. Always double-check which bucket you're targeting before hitting enter. and verify the exact command behavior in the current documentation. Pause and recall. What's the minimum storage duration for nearline? 30 days. A small delay for a big cost drop. Now that object storage is second nature, let's shift gears to block storage. Think of persistent disk as the virtual hard drive you attach to a compute engine VM. The key thing beginners often miss: it lives independently from the VM. When you delete a VM, the disk stays, unless you check the box to delete it too. That means your data survives the VM's death, exactly the opposite of a local physical drive. And just like GCP's per-second billing for compute, you only pay for the time the VM runs, the disk itself is billed per gigabyte month, completely separate. So you can stop the VM to save money, and when you start it again, your data is still there, untouched. Here's the architecture that saves your data. When you delete a VM, the persistent disk doesn't automatically vanish. For a production database, you could delete the VM entirely and still restore your database from the unattached disk later. That's the independence you need. Compare that to a local SSD, which is physically attached and disappears with the VM. Always verify the delete boot disk. Checkbox is unchecked when you don't want to lose data. A high IOPS persistent disk can cost significantly more per gigabyte than object storage for the same capacity. At scale, that difference balloons into a massive monthly bill. Many beginners treat all storage as equal and end up with shocking invoices. Always match the storage service to the data's access pattern, not just the labeled disk. Let's talk IOPS, input-output operations. Per second, the number of read-write operations a disk can handle per second. PD standard HDD typically costs the least per gigabyte and works well for sequential workloads like batch archives. PD-balanced SSD offers a good balance for web servers. PD SSD provides higher IOPS for responsive databases, which often comes at a higher per GB cost. PD Extreme allows you to provision even more IOPS for demanding transactional systems like SAP HANA, but you pay extra for those provisioned IOPS on top of capacity. The rule of thumb: match the disk to the workload's performance appetite and don't pay for IOPS you never use. Quick checkpoint. Which persistent disk type is the most cost-effective for high-throughput, sequential writes? Pause and picture your nightly archive jobs. It's PD standard HDD, the cheapest per gigabyte, with enough throughput for batch work. Now let's see how to resize a disk without any downtime. Cloud spend often balloons because of over-provisioned disks. This trick fixes it instantly. Run the gcloud command to resize the disk while the VM stays running. No reboot needed. Then log into the VM and extend the file system. Use resize 2Fs for ext4, the default Linux file system, or XFS, growfs for XFS, a high-performance alternative often used with large file systems. Your application sees the new space. That means you can start small, monitor usage, and scale up only when needed, never paying for unused gigabytes. NVMe, or Non-Volatile Memory Express, is a high-speed flash interface that slashes latency. Local SSD uses physical NVMe drives attached to the VM, blistering IOPS, but stop the VM and the data is gone. That makes it perfect for temporary data like a Hadoop scratch directory, never for anything you can't lose. Persistent disk is your safe, durable block storage, a bit slower, but it hangs around through stops, terminations, and zone swaps. Choose local SSD when you need raw speed and can rebuild data. Choose persistent disk for everything else. Quick checkpoint. If you store critical data on a local SSD and the VM stops, what happens? Typically, it's gone, unless you've explicitly preserved the local SSD during the stop. Ephemeral storage is pure speed with no durability guarantee. Now let's look at a shared file system that bridges the gap. Here's a common cost trap. Companies spin up Filestore for workloads that don't need POSIX, the portable operating system interface standard that guarantees consistent file access and locking across Unix-like systems. Paying a premium for NFS when object storage would cost far less. Let's see the right architecture. Filestore provides a managed NFS file server. At the center sits a Filestore instance, Compute Engine VMs, and Google Kubernetes Engine, or GKE pods, a managed Kubernetes cluster, all mounted via NFS, reading and writing the same files simultaneously. No data duplication, no NFS administration, and no costly silos. Filestore provides fully managed NFS file shares, but it's not always the right answer. Run through this checklist to decide if your workload truly needs POSIX semantics and shared file access. If you check most of these boxes, Filestore likely fits. A common trap. You have multiple VMs and immediately think you need a shared file system, so you reach for Filestore. But ask yourself, do these VMs truly need to read and write the same files concurrently with POSIX semantics? POSIX, Portable Operating System Interface, guarantees file locking and shared semantics across Unix-like systems, essential when multiple processes touch the same file without corruption. If your app doesn't need that, skip the complexity. This checklist helps you decide. Let's lock this in. Your web app runs on 3 VMs, each writing access logs to its own boot disk. Do you need Filestore? The answer is no. Each VM writes independently to local storage. There's no need for shared POSIX file access. Object storage or a log aggregator is more cost-effective. Start by creating an incremental snapshot with the gcloud disks snapshot command, specifying a snapshot name and zone. You're only billed for the blocks that changed since the last snapshot. Then, to restore in another zone, create a new disk from that snapshot in any target region. Snapshots are global, so you can replicate across the globe. This is the most cost-effective way to relocate a data-heavy VM because you avoid data transfer costs of moving a live disk. Finally, attach the new disk to a VM in the target zone. Here's the snapshot workflow. You create a snapshot from a source disk in US Central 1A. In GCP, snapshots aren't tied to a specific zone. You can use them to create a new disk in any zone or region, like Europe, West 1B. That's cost-effective zone migration without moving live data. To catch runaway storage costs before they surprise you, set a budget alert. In the Cloud Console, go to Billing, then Budgets and Alerts. Create a new budget, specify a monthly amount, and configure email notifications at 50, 90, and 100% thresholds. Let's quickly test your bucket knowledge. You try to create a cloud storage bucket, but you get an error. What's the likely cause, and what command did you run? The answer: you used gsutil-mb, and the bucket name was already taken. Bucket names must be globally unique across all of Google Cloud. Pick another name. Let's assemble the decision matrix into a real production architecture. Users hit Cloud CDN first. Static assets like product images are served straight from a cloud storage bucket. Cache misses land on a GKE frontend. That frontend mounts Filestore for shared WordPress content, then queries a Cloud SQL database, GCP's fully managed relational database service for MySQL, PostgreSQL, and SQL Server, backed by a persistent SSD, and ships every application log to a separate cloud storage bucket governed by a lifecycle policy. Here's your quick reference command sheet. 10 commands you'll type every day when building real GCP storage environments. Bookmark this timestamp, run each one in a sandbox this week, and they'll become muscle memory. If compliance is on your radar, dig into bucket lock and object holds. Those are GCP's worm primitives. You lock a bucket with a retention policy, and even the project owner can't delete or overwrite objects until that policy expires. Object holds let you freeze individual files. These exact features show up in the Professional Cloud Architect exam, so tuck a flag on them now. You'll thank yourself later. Those 4 rules are your storage playbook for every GCP project. Match frequency to tier, set lifecycle policies, treat snapshots as intra-regional, and lean on IAM. You've now got the storage half of GCP architecture fully mapped. Object, block, file, lifecycle, and security. That's a massive step toward designing real systems. Now that storage is locked down, it's time to wire everything together. The next video dives into VPC and networking, how GCP's global VPCs work, how to carve out subnets, how Cloud Router dynamically exchanges routes between your VPC and on-prem networks, and how to connect your on-prem data center without a mess. Hit subscribe and the bell. This series only gets deeper. Don't just watch, apply. Sketch out the storage for this startup stack on paper or in a comment below, and I'll see you in part 5.